Okay, so good afternoon. Today I'll try to finish talking about uniprocessor scheduling. So we were talking about FCFS and round robin. Now we discussed how changing the length of the time quantum affects the I'm sorry. Yeah. So we discussed how the changing the length of the time quantum affects the average response time. So now let's continue with our discussions about round robin. Now, so the actual choice for the time quantum really depends on system and the costs. Really it boils down to the cost of context switching. Initially, in early Unix systems, it was around 1 second, but you can see that that wouldn't really work well with today's system. Let's say if you move your cursor and it's going to take one second to see that effect on the screen, that's absolutely not responsive. So these numbers that you see are a little bit more up to date. So it's usually something between 10 millisecond to 100 millisecond, and this is because of the cost of context switching. So you usually want to keep the overhead low, right? So if you're gonna run for Q and then spend a delta time for context switching for then running another queue, then you want really the delta divided by Q plus delta to be less than, let's say, 1% or something like that, right? So you set a target in terms of how much overhead you want to have, and then you measure your context switching time, and then based on that you set your Q. So you set the maximum Q to, so you measure context switching overhead, and you set a target latency, target overhead, and then that gives you Q. So you want the overhead to be roughly 1%, or depending on the system that you're designing, that could be 1, 5, even less than 1%. Okay, now is round robin always better than FCFS? So that's a loaded question. What do you exactly mean by better? But let's compare round robin with FCFS. I'm going to put I'm going to consider a specific workload. So in this workload, I have 10 tasks, and each one of them takes 100 seconds of CPU time. Let's look at round robin if the time quantum, the length of time quantum is 1 second. So in that case, this is what's going to happen with FCFS. So FCFS, let's assume that tasks are ordered with their number. So T1 is going to run first, T2, and all the way to T10. So that's going to be the schedule and the outcome under FCFS. So this is what's going to happen. Now, if you look at round robin with time quantum size of 1 second, then this is going to be the schedule, and the T1 is going to finish at 991, T2 is going to finish at 992, and T10 is going to finish at time 1000. So these are the completion times, Now, assuming that all tasks were in the system from the beginning, you can see that we have this equation inequality all the way through. So this is basically the response time under round robin, and this is the response time under FCFS, and the response time under round robin for all of them is more than the response time under FCFS. So overall, round robin is going to give you a really bad response time, average response time, compared to FCFS, which gives you a better response time. And in this particular example, actually, FCFS is giving you the best response time possible. And so if the metric that you want to compare is average response time, at least we found one example where FCFS is doing much better than round robin. Now, if the metric that you want to consider is fairness, how fair round robin is against FCFS. Now you can actually observe here that round robin is really fair in terms of response time, right? So all tasks have similar response times. So all of them are, so the difference between response times of tasks is less than 10 seconds. Whereas the difference between response time under FCFS is all the way to 900 seconds. So the response time of T1 is 900 seconds less than the response time of T10. So FCFS is really unfair to T10, but round robin is really fair to everyone. So there is less variance in terms of response time. So that's something to consider. Give me a second. So if you have, so these two cases are happening because I'm assuming that the context switching overhead is 0, right? So if you had a context switch overhead that was more than 0, then FCFS would incur 9 context switches, whereas under round robin we have 10 times 100 context switches, or maybe 9 times 100 context switches. So the number of context switches in round robin is a lot more than, it's 100 times more than FCFS. But without that, both of them are going to finish at the same time. Average response time under round robin is really bad. Also, if your system has caches, right? So if you have a CPU and then the CPU goes to cache level 1, L1, and then L2, and then L3, and then eventually it goes to memory. Now you start running T1. T1 brings its data in cache. Now, if you context switch to T2, now T2 doesn't have its data in cache, so it has to bring its own data to L1. So it's going to kick T1's data out. Now, when it comes for T2 to now benefit from the data that it has brought to L1, you're going to context switch to T3. So, and then by the time you come back to T1, the data that T1 had in L1 is all gone. So T1 has to now again access memory. And you end up seeing all your tasks going to memory instead of going to the caches. Because every time they bring their data, you're going to context switch to someone else. And that someone else is going to kick the data out of cache and bring their own data. And this cycle is going to continue all the time. Whereas in FCFS, when T1 brings its data in cache, it gets to use that data until it finishes. And then T2 pays a little bit of cost to bring its data into caches, but then it uses it until it's done. So if you really measure the overhead of round robin, it's going to be much more than just paying the cost for context switches. It's also going to be the time that the tasks are going to waste. Instead of accessing their data in L1, they're going to access their data in memory, which is a lot more expensive. Okay, now let's have a better comparison of round robin and FCFS in the sense that let's look at a variety of time quantum sizes. So the best, I'm bringing back the example that we saw before, where we had 3 tasks, and they had different sizes. So if you go back to the slides before, this was a workload that we considered in the past. So T2 is the shortest task, and then T3 is the longest task. And this is the best in terms of, this is the best outcome if you care about response time. So if you care about response time, you need to execute the short tasks first. So T2 first executes and gets done, then you move on to T4, T1, and then T3. So this is the best outcome if you care about average response time. And this is going to give you these numbers. So the best wait time is going to be for T1, the best wait time is 32. The best response time is 85, and so on and so forth. For T2, the best wait time is 0, and the best execution time is 8, and again, so on and so forth. So average best FCFS gets 31.25 in terms of average wait time, and 69.5 in terms of average response time. Now, worst case is the reverse order when you start executing the longest task. In this case, the short tasks have to wait for the long tasks to finish. This gives you the worst case FCFS. So in terms of average wait time, it's going to be almost 3 times more, and in terms of response time is almost 2 times more response time in the worst case scenario. Now you can so in this particular example that you can see, I fixed the length of time quantum to 8, and this is going to be the schedule. We go P1, P2, P3, P4, and then we come. I guess this should be T1. Sorry for that. So it's going to be T1, T2, T3, T4, and then you come back T1. At this point, T2 is done, so you go to T3 and then T4, and so on and so forth. So this gives you you can calculate wait time and response time for these 2 cases, and you can actually populate this for all the other quantum sizes. Now, when you look at this table in this slide, you should look at these 2. So let's look at T2. So T2, you can see that the numbers are really different. You see a lot of variance in T2's wait time and T2's response time across different time quantum sizes. So basically, T2 is very sensitive to the response time. Sorry, to the size of the time quantum. As you change the size of time quantum, the response time of T2 changes dramatically. Now compare that with T3. So if you look at T3 is absolutely not impacted by the change of time quantum, the length of time quantum. So across the board, I mean, not considering the worst case FCFS, across the board, it gets the same numbers. And to just remind you, T3 was the longest task, and T2 was the shortest task. So the takeaway here is that if your task is really long, then it really doesn't matter how short or long the length of time quantum is. If, and this if is important, if the context switching overhead is 0, because if context switching overhead is non-zero, then these numbers would be different, definitely. So the conclusion I'm making is if the length of time, if the overhead of context switching is 0. But if you are a short task, then you're very much affected by the choice of the length of the time quantum. Okay, now we're done with the first two scheduling policy, FCFS and round robin. The third scheduling policy we're going to talk about is shortest task first. So as the name suggests, this is going to be running the shortest task first. And this is there to mirror the best FCFS scenario possible. If you remember, as I said, you want, if you care about average response time, you should just sort your tasks based on their execution time and start running the short ones first. That gives you the best response time. So that's basically this scheduling policy, which is shortest tasks first. And it's actually sometimes called STCF, which is shortest time to completion first. So every time we look at how much time is left to complete this task, and we pick the shortest one, the one that has the least amount of work to complete. And this is when you don't want to preempt. So somebody is asking a question, dumb question, why is the acronym for shortest task first SGF? I hope that answers the question. It's shortest job first. Good question though. So SGF is shortest job first, but in the context of my lectures, I'm using task, and as I said at the beginning, I'm using these terms interchangeably. But anyhow, so then so this one is without preemption. So you know, every time you want to make it this, every time a task exits the system, you basically, give me a second. System is messed up. So anyhow, okay, so yeah, so in shortest task first, every time you finish a task, you look at all the other tasks and then you pick the shortest one. In shortest remaining time first is the preemptive version of that. So every time a new task comes in, you might want to then context switch to the new one if the new one is shorter than the one that you're running already, right? So in this one, if you're running a task and a shorter one comes in, because you don't have preemption, you just continue with running that whatever you are running, and once you're done, then you run this shortest one. With preemption, if a shorter task than the one that you're running comes in, then you start running the shorter one. Now you can, so going back to the model that we had for our tasks, where they would do a CPU burst and then they would go for I/O and then they come for CPU burst and so on and so forth. We're going to apply this to each CPU burst. So every time a task goes for I/O, it's gone. So we're not going to consider that. So when they come back, we look at their next burst and we compare that. So we compare the length of the next CPU burst among all the tasks that we have. Now, you can prove, I'm not going to run through the proof. I used to do, but it takes some time. You can actually look at the proof. It's not going to be that hard. So you can prove that this policy minimizes average response time for any workload. So no matter what your workload is, if you apply SGF or SRTF, you're going to minimize average response time. So you can do like prove this by contradiction. Say, if I don't run the shortest task and I run something else, then my average response time is going to go up. So that's how you prove that this is optimal. Meaning that if you want the lowest, then you have to run the shortest first. Now, so it's provably the best for average response time. So it's provably optimal. Now, if you compare SRTF with FCFS and round robin, if all the tasks are equal size, then SRTF and SGF, they don't say anything because, you know, for them, all of them have the same priority. FCFS the same, right? FCFS also doesn't care about the length. It just cares about the arrivals. So if tasks have the same length, then SRTF and FCFS, they have the same outcome. And because we know that SRTF is optimal in terms of average response time, so FCFS becomes optimal. So if the tasks have the same size, then doing FCFS is the best you can do. Now, there are theorems that state this in a stochastic system as well. So if you have a stochastic system where tasks arrive stochastically with some distribution, but then if all of your tasks have the same, the length of the tasks have the same distribution, so it's identical and independent across tasks, then again, FCFS gives you the best average response time in that case as well. Okay, so if tasks have varying sizes, then of course FCFS could lead to terrible average response times depending on the order of the arrivals. So some cases it could be really bad, in some cases it could be really good, depending on the arrival, because FCFS has the tendency to get short tasks stuck behind long tasks, and that hurts the average response time. Let's run an example and compare FCFS, round robin, and SRTF. So in this workload, I have three tasks, A, B, and C. A and B are really long. Let's say they have a CPU burst that lasts for a week, each one of them. So if you start running them, it lasts for a week to complete. And let's assume that task C has this, this repeated behavior where it does 1 microsecond of CPU burst, and then it goes for 9 microsecond of I/O burst, and this repeats for task C. Now, if you run these guys by themselves, so if you only had if your workload only had A, then you would run A, and that gives you CPU utilization of 100, because during this week your CPU is going to be all busy running task A. The same with task B. So both of them give you CPU utilization of 100%, but both of them are not going to do any I/O. So you get I/O utilization of 0%. If you run C by itself, it's going to utilize your CPU by 10% because it's going to do CPU burst of 1 microsecond and then go for I/O for 9 microsecond and then come back. Sorry, millisecond. So CPU utilization is going to be 10% and I/O utilization is going to be 90%. Now that we have a mixture of the both, so we're hoping that we get this 100% CPU utilization and close to 90% I/O utilization. So let's say how different policies do. If you do FCFS, depending on the order of these tasks, you could see the first few allocations being different. So best case scenario, C comes first. So C runs for 1 microsecond, and then it goes for I/O. At this point, we're going to grab A or B, but each one of them we grab, we're going to be busy for one whole week until it's done, and then another week for the next one. So the response time of C is going to hurt a lot, even if C comes first. If C comes third, then it doesn't even run that 1 microsecond. It has to wait for A and B to be done to then start running C. So this is going to be really poor average response time. If you do round robin and SRTF, what's going to happen? So this is going to depend on, at least for round robin, it's going to depend on the length of the time quantum. So let's look at it. So let's assume that the length of time quantum is 40 microseconds. So in this case, let's assume that C is first. So we're going to run C for 1 microsecond, and then C is going to go for I/O, and then we'll come back. So when C comes back at this point, it's going to go behind B. So we're going to have A, B, and C. So we're going to run A for 40 microseconds. Then we're going to run B, and then we're going to run C again. It's going to run for 1 microsecond, go for I/O, come back. So this is going to be how it's going to look like. Now, if you look at I/O utilization, it's about 11%. CPU utilization is 100%. Now let's look at round robin with 1 microsecond time quantum. So in this one, C is going to run for 1 microsecond, and it's then going to go for I/O. While it's going for I/O, A and B are going to run each one of them 1 microsecond and then switch between them because C is now out of the picture. So we're going to do A, B, A, B, A, B, A, B, B, and then C gets to run again. So this is how it's going to look like. And as you can see, there is this 1 microsecond here that C comes, but then goes at the back of the list, right? Because it's a newcomer. So it goes to the back of the list and then waits for its turn to come to get I/O. So this gives about 82% I/O utilization. Now, how does SRTF do for this particular example? So C is going to run. It's going to go for I/O. While it's going for I/O, we're going to choose between A and B. Because both of them have the same length, then it doesn't really matter which one we choose. Let's say we choose A. And then the moment C comes back, it preempts A because it's the shortest one, because its CPU burst is 1 microsecond. Excuse me, 1 millisecond. So C is going to interrupt or preempt A, and it's going to run. And then it's going to go for I/O, and we then start resume A, and so on and so forth. And B is going to, wait there for its turn to come, and A is going to keep interrupted by C. Now this gives us, CPU I/O utilization of close to 90%, or actually exactly 90%. So, and it's going to be the best in terms of average response time, because SRTF is proved to be the best for response time. Now, what are the problems with SRTF? The first problem is the starvation of large tasks. So as you saw, for example, in the last example, task B and A might get starved if we have a lot of C's, right? Let's say I have 10 C's in the system, 10 instances of task C. Then those instances are going to be always preferred to A and B. So A and B will always wait for them, and if we have enough of those C tasks, then A and B are going to starve. The other thing is the overheads. So every time C comes, right, it requires a context switch. So you're going to have a lot of context switches if short tasks come to your system very frequently. Every time they come, you have to have a context switch and give them the CPU. And the last one is basically very related to the starvation. In the first one, you're basically having to penalize large tasks. So the fact that you're starving them, it means that you're not fair to them. But more importantly, the most serious problem with this SRTF is that it's impractical, because up to this point I kept saying, I know the length of the CPU burst of my tasks, but it's really not clear how you would know that, right, up front. So predicting how long each task takes is $1 million question in computing systems. We normally often have no idea how long our tasks take. We might have some, we might do some profiling, and that might help to, have a bound on how long a task could take, but it's usually very hard to know exactly how long each task takes. So as a result, in reality, you cannot implement SRTF, STF or SGF or SRTF. Yeah. If you insist on wanting to predict, then you could potentially for your system use some notion of, using some machine learning technique to make predictions about the length of your tasks given the previous observations that you have had of your task. So for example, in the case where we had this task C, let's say initially I didn't know how long it takes for it to run on CPU and how long it takes for it to go for I/O. I could just observe, I can just, make some observations. And then if I see this is reoccurring, that C just goes for 1 millisecond of CPU burst and 9 millisecond of I/O burst, then I can conclude or predict that next time this is going to be the case as well. This prediction may or may not be accurate, right? Because maybe C had a while loop for 1,000 times, it was doing something, and after 1,000 times, it's going to do something else, right? So I make some prediction when it's doing that 1,000 times, but then my prediction would be not accurate at once C is done with that loop and it starts another phase. So that's the caveat. So you could predict, but you always have to put some chance on your predictions not being 100% accurate. So in terms of prediction, we usually are talking about this function that gets the execution times, the previous execution times last time, all the way. So these are the history. data, right? So how long this task's CPU bursts were so far, and then I could have like a function that uses that data to make a prediction about future. One of the most common functions, you could use a neural network here, right, to get previous data and then make a prediction. You can have time series analysis. You can do all sorts of crazy stuff here, right? Of course, whatever F is, you know, it should be lightweight. If you're using this for scheduling, you don't want to spend a lot of time calculating this F before you make a decision on which task should run next, because then the overhead of scheduling would increase, right? Let's assume that this F is a neural network and you have 1,000 tasks, and then you have to, you know, make predictions, make inferences with your neural network for 1,000 tasks before you make a decision which one of them should run. And that could take like a considerable amount of time, and that's really bad, right? So you really want this F to be lightweight, like few cycles, and then you have a prediction. One of the, again, most common ones is the exponential averaging. So basically, you say my prediction for next time, Tn, is some fixed ratio times what happened next time previously. So whatever was the previous execution time, Tn minus 1, plus, so let's put this is my prediction. So I'm going to put tau for my prediction and t for the history. So this is my prediction, and this is the actual time. This is the history at time n minus 1. And then you put 1 minus alpha on your previous prediction, whatever you predicted previously. So you say, you kind of like, you know, put weights between what really happened next time previously and what you predicted to happen previously. Now, if let's say this alpha is 1, if alpha is 1, then you're just ignoring your previous prediction and you're saying, you know, my prediction this time is whatever happened last time. So if last time it took 1 second, so my prediction for this time is also 1 second. If this alpha is 0.98, then you're saying with 98% chance it's going to be whatever happened last time, and with 2% chance it's going to be what I predicted last time. And if you analyze this, it's kind of like it's an average of the last, I think with 98, I think it would be the 20 previous, you're kind of getting an average of the past 20 times. I mean, I can write it down for you, but because it's like, let's say T20, sorry. Tau, let's say you're at time 20. This becomes 0.98 T19 plus 0.2, sorry, 0.02. So 0.02 times tau 19. But now what was tau 19? Tau 19 was 0.98 T18 plus 0.02 tau 18. Now, what was tau 18? It's going to be 0.98 T17 plus. So you get the idea. So this becomes 0.98 T19 plus 0.02 times 0.98 T18 plus 0.02 to the power of 2 times 0.98 T17 plus blah, 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 which is the geometric sum of T19, T18, T17, and so on and so forth, with the step size being 0.02. So after, let's say, 20 steps, this is going to be so small that you're kind of like forgetting about very long histories. So that's basically what this does. And this is very famous. It's used everywhere. You know, even in today's machine learning techniques, in optimization techniques for gradient descent, this is used, right? For those of you who know what gradient descent is, you know, you get the derivative of your function and you want to move towards the derivative of your function. Usually making that move, if you get a stochastic gradient, is going to be leading to a lot of moves back and forth. So in order for you to smooth it out, you, instead of using the exact gradient, you use the exponential sum of the previous gradients. So if this round's gradient is this way and previous round gradient was this way, you kind of get the average of it. And that gives you a smooth convergence to the optimal solution. It's also used in, you know, TCP IP protocol for congestion control, and so on and so forth. It's very, very famous, and it's pretty lightweight. So doing this calculation, you can probably in general purpose computers do this in few cycles. It's just an addition and bunch of multiplications. Now, I'm going to sort of move on from this application type thingy. So I don't. One thing about this is, so the takeaway from this slide and the next slide is, some people use the information they get from application CPU bursts. So they run their system, they measure the CPU bursts of their applications, and they might do some predictions, as we talked. But one thing that some people have done in the past is to make inferences about the type of the application that they're running. For example, if you get an application that has really short CPU bursts and long I/O bursts, one fact that this might imply is that maybe this application is an interactive application, right? Maybe this is an application where the user puts a command and then you do a bunch of things, and then another command and another bunch of things. So maybe it's that kind of application. And once you make a decision on what kind of application this is, you might want to use that information to schedule these tasks. So in the pure way of, like, you know, in the FCFS, you might actually just use the length of the CPU burst, whatever you predicted, to then schedule. But in more general cases, you might say, oh, this is a gaming application, or oh, this is a streaming application, or this is like a matrix multiplication, it's a AI application. So you might classify your applications, and then based on that classification, decide you want to have more priority for streaming application or gaming application, and less priority for, you know, if this is kind of like a background kind of application. Now, this might look attractive to do such a thing, right? To kind of classify application and then enforce some notion of priority based on what you infer. But you have to be really careful, because it has been actually tried before. Very distinctively, it was used in one of the previous mainstream schedulers in Linux, in particular O1 scheduler, was doing the same thing. So it was measuring the previous bursts, and then it inferred something about the application, and based on that inference, it prioritized some tasks, but it failed miserably, and it was replaced in short time with another scheduler, because there is always an error in your prediction, right? there is an error in predicting the CPU burst, but also there is an error in predicting types. So you might think that your application is a streaming application, or is a gaming application, or is a interactive application, and maybe it is not. Maybe it is acting like one, but it's actually some other application. And if you make a wrong prediction and then base your scheduling on that wrong assumption, you might mess up your system. And that's precisely what happened in O1 scheduler. So they made some priority adjustments based on these predictions, and those priority adjustments ended up backfiring and giving users a really bad experience and bad response time. So it was very short-lived, the O1 scheduler, and it was substituted with another better scheduler that was not doing this kind of prediction and inference. So the takeaway is, it's really hard to look at history and then make decisions about the type of your application or characterize your applications. It's a hard thing to do. And unless you're forced to do it, it's better not to do it. So unless in certain, use cases that might be justified, but generally speaking, it's not. So don't try it. Okay, so final notes on SRTF. It's the best in terms of it's optimal in terms of average response time, but it's not practical because it's hard to predict the future. It's also, it might incur a lot of context switches, and it's also unfair for long tasks. So that was the third scheduling policy. Let's move on to the fourth one. This is pretty much similar to what you guys implemented for your labs. It's called a strict priority scheduling. So you have a set of priorities and you want to prioritize tasks with higher priority compared to the lower priority ones. The reason that there is a strict here, it means that as long as you have high priority tasks, you're not going to run the low priority ones. So that's where the strictness comes. As we will see, you could drop this strictness and start, executing some of these guys, even if you have high priority tasks. But with the strict priority, basically the functionality of it is as if you have these separate queues, and then you're putting tasks with different priorities on different queues, and choose between them. So you might want to do anything you want. You can do per queue, right? So you could potentially do round robin between task 1, task 2, and task 3, or you could do FCFS, or whatever else you want to do. You can randomly choose one. It doesn't matter. So across tasks with the same priority, you enforce some notion of a scheduling. Again, round robin, FCFS, random, whatever, doesn't matter. But then, as long as you have high priority tasks, you're not going to go to the low priority tasks. Now, any problem with this? Well, obviously, this leads to a starvation. So if I keep getting high priority tasks, I would never ever go to the low priority tasks, and they will get starved. So that's first. Second is that this could lead to priority inversion. So I kind of ignored this last time, but maybe I should explain what priority inversion is. So I try shortly to explain priority inversion. So let's say you have 3 types of tasks: low priority, medium priority, and high priority. So this is time. Let's say your low priority task, so let's say there is no other task in your system, you run your low priority task. And let's say at this point, your low priority task locks a mutex, for example. So it says mutex.lock. So it locks the mutex and then it continues until it gets interrupted by a high priority task. So we interrupt, we start the high priority task. So because this is a strict priority, so we're not going to come back to L, we're going to just go with H. Now let's say at some point here, H also does mutex.lock. Now what's going to happen is, well, the mutex is locked by L, right? The low priority one. So H is going to go and wait. So H is going to be put into waiting. So H will go waiting. And we come back to L. So we start doing L. So L still is running with the lock. Now let's say at this point M comes. So L gets interrupted and M starts running. So what happened here? So right here we have priority inversion. The reason we have priority inversion is because now this M task is preempting this L task, but this L task previously preempted or somehow made the H task to wait. So this M task now, sorry for that. So now this M task is indirectly getting a higher priority than this H task. So this is where the priority inversion comes in. So again, priority inversion happened because this M task was able to preempt the L task. And as a result, indirectly, now H task is waiting for this M task. It was fine for this H task to wait for this L task because L task was holding the lock. So that was fine. But this M task is not holding any lock, right? But again, H has to wait for M to finish so that L can run and unlock the mutex so that the H can continue. So this is priority inversion, and it happens if you have a strict priority scheduling. So I ended up explaining priority inversion as well. Okay, so I got a question. Do we have to predict what type of application it is? Can't the application give us some sort of metadata to determine this? In regard to application types, sorry, realize I'm a bit behind in terms of time. Right, so that's a good point. So in reality, we do allow that with these priorities, right? So instead of us predicting the type, we allow users to tell us by just setting these priorities. These are exogenous. Instead of we going and predict types and then give priorities, we leave that to user. So we ask users to let us know what priority each task has, and then we just stick to that. So we just go with those priorities. In a context that we will see later on, we can also use weights. So instead of saying high priority, low priority, medium priority, we can ask users to put weight on each task. And let's say if one task gets weight 10 and the other task gets weight 5, this tells me that the first one with weight 10 is twice as important as the second one. So I would be interested in the relative, the ratio between weights, and that's also possible. So yes, instead of we predicting and inferring types, it's better to ask the users to just let us know by indicating their priority or indicating some notion of weights. And that's usually done in modern systems. So in modern systems, in data centers, in operating systems, you usually allow users to, you have an API for users to tell you their weights. And in Linux, it's done through C groups, for example. For those of you who are interested, you can look at it. So you can specify weights for your tasks and threads and processes. And the operating system enforces those through C groups in Linux. OK, now a strict priority, it's kind of unfair because the low priority tasks are going to suffer and starve. So this is an example. There was this Multics, I think, is an MIT operating system, if I'm not mistaken. And when they shut it down, they found a task that was sitting there for 10 years. So it had really low priority, and it just got starved forever. So if you move on from the strictness, one thing you could do, instead of having a strict priority, meaning that instead of finishing all the high priorities before you go to the low priorities, you can, one option, if you care, is to divide time between different priorities. So you could potentially say, you know, let's say 90% of the time I schedule tasks from highest priority, and then maybe 15% of the times I schedule tasks from medium priority, and 5% of the time I schedule tasks from low priority. This way, at least you prevent a starvation, right? So that's an option. Yeah, so that's an option. So the other option that you could do is, if you have a low priority task that has been sitting in there for a long time, then you can elevate their priority. So that's also a possibility. If you don't want to do this, you know, fractions of time scheduling from different priorities, you can elevate people's priority if they're waiting for a long time. So that's also possible to avoid a starvation. You can just inflate their priority so that at some point they get to the high priority queue and get executed. So this is another example where fairness and performance are going to clash, right? So, you know, if you really care about fairness, then you don't want tasks to starve, and you might have to schedule them, even though that might hurt your throughput or your response time. Now, this brings us to the, I think this is the 1, 2, 3, 4. This is the 5th scheduling policy that we're going to talk about. It's called multi-level feedback queue. So we want to get the best of the two worlds. So if we care about fairness and we also care about response time. So if you care about response time, you want to do the short tasks first. That we know. That will help our response time. That makes our system more responsive. Because if a task is short, I'm going to just do it right away, and that is good. Now, if we just do that, we're going to hurt fairness, because then the long tasks are going to be penalized. Now, how can we get the best of the two worlds? How can we get to run the short tasks, but also not starve the long tasks? And this is a motivation for this multi-level feedback queue, which tries to achieve that. The way it achieves this is, it's very similar to the strict priority. So I have a bunch of queues, and these queues indicate some notion of priority. So the higher the queue is, the more the priority is. But instead of putting tasks in each queue and making them stick there, we're going to move tasks between these queues. So when a new task comes, a new task goes to the highest priority queue. And at some point, it gets scheduled. We're going to do round robin in the top queues. And the bottom queue, we probably want to do FCFS. Now, the length of time quantum changes across queues. So we have short time quantum lengths at the beginning at high priority queues. And if you remember, FCFS was round robin with infinite time quantum size, right? So basically, the length of time quantum increases across these queues. Now, if a task comes to the top of the list and gets scheduled, if the time quantum expires and the task still has work to do, what we will do is that we move the task to the next queue. If the task is done, then good, it's done. So it just exits the system. With this way, if you look at it, and stare at this a little bit, you'll realize that this is actually doing what we really wanted. So if you're a short task and you come to the system, you're going to be prioritized. You're going to go on the top list, and eventually you're going to run. Now, if you're really short, then the time quantum in the first 1 or 2 queues are going to be enough for you. So you will get out of the system really fast because you get high priority and you get out. Now, if you're a long task, this system eventually pushes you down, but then in the process of you being pushed down, you get to run, so you don't starve. And that's where we get both the best of the both worlds. We get to run the short tasks fast without starving the long tasks. Now, you don't necessarily need to do round robin here. You can do other stuff. You can randomly pick between the tasks in each queue and then run them for a time period and then push them down. When it comes across queues, you can do what we talked about. You can do time sharing. So you can, for example, spend 90% of the time on the top queue, let's say 80% of the time there, 15% of the time in the middle one, and then 5% of the time in the bottom one. So that's also possible. Now, the specifics of this, right? These the policies, how it will depend, right? So there are so many parameters to set. So I'm just giving you the big picture, the big idea. There are so many parameters to be fixed. So there are many variants of multi-level feedback queue. Now, one of the earliest versions of this. So let's say a task comes in and finishes. Let's say C in the example that we had before with 1 millisecond CPU and 9 millisecond I/O. When C comes, I'm going to put it at the first queue, and the time quantum is 8 millisecond, let's say. So C is going to run for 1 millisecond, and it's going to go for I/O. Now, when it comes back, the question is, where should I put C? One thing is, every time they come back, you just put them on top. So that's one option. So you always put them on top. The other option is to, keep some notion of like tracking how long they have run in each one of these queues. So that's another option. So yeah, we talked about this, dropping them off. One thing that you could do, let's say C is here. Let's say, you know, somehow C was pushed to the second one, and now it goes for IO. Do you want to put it back in this queue when it comes back, or start from top again? So these are all options that you have. You can decide what you want to do, right? So let's say a task is here, FCFS, so it has been pushed all the way down, and now it goes for IO. And when it comes back, do you want to put it, you know, in the first one, you want to put it here, or maybe you want to elevate it one level, or 2 levels, or 3 levels. So these are all options that you have to make a decision. Right. So overall, this gives us the approximate SRTF, and it also gives us good fairness. So to schedule between queues, you can just do fixed priority scheduling, meaning that as long as you have tasks in the first one, you just run it before moving to the second one, before moving to the third one, or you could do time sharing, as I said. So you can just divide your time between these queues. Now, the last thing I wanted to talk about is whatever decision you make, right? Whatever, you know, policy you set. As I said, there are many parameters to be set, right? Like how you're doing a scheduling among tasks within each queue, how are you scheduling across queues, where you put tasks when they come in, and so on and so forth. So these will have implications. So one example, so this was actually used at MIT servers, this multi-level feedback queue. And the way that it was implemented in that system, it was like whenever a task would have IO and it would come back, they would put it at top of the list. So it would get the highest priority. So there was a contest in MIT, and people were playing, like different groups had programmed, you know, had coded these intelligent programs that would play the game of Othello, or you know, this could be applied to any kind of, you know, program, right? But there was a competition, so it was a zero-sum game. So if you win, I lose. If I lose, you win, or if I win, you lose, right? So there was a competition. Now there was a server that different groups would run their code on the server, and then these two programs would compete. Let's say game of chess, the first program would make a move, and then the second program would make a move, and so on and so forth. And then one program eventually would win the game. Now, there was this smart group that knew about this scheduling policy, and they misused that information, if you wish, for others, but for their own sake, it was a great usage. So they put these printfs in their code, and printf is basically IO, right? So every once in a while, their code would do a printf, and this printf would elevate the priority of their code. So therefore, their code would get to run on the CPU in this machine more favorably than other contestants. So other contestants' code would be pushed down this queue because they didn't have any IO. They probably did have, you know, a bunch of computation to do, but these guys kept their task up here. So as a result, their task was getting more CPU time, and the more CPU time you get, the more computation you could do in terms of solving the game, right? Usually, like game of chess, it has a really big state space. You make a move, then your competitor makes a move, then you make a move, and so on and so forth. And like it has a long history until you win. And you never can, get to the bottom of this tree because it's so big. So you have to cut it at some point. And then you have to look at this and then have some scoring, notion that looks at this estate and says, how good is this estate for me? Now, the more time you get on CPU, the further you can push this line down. And the further you push this line down, the more accurate you can score that estate. Like if I look at the chess and I make one move, it's hard to put a score on that. But if there are only few moves left to the end of the game, then I can have a more accurate score. So anyhow, these guys were misusing this information in their own benefit to get basically to win the game. And this is an example where I always tell students that the decisions you make in how you allocate resources in your system has implications, right? And you have to make those decisions very wisely so that you can, have a robust scheduling policy or robust allocation policy to guard against these kind of behavior. Okay, so next move on. The sixth, how many is this? The sixth? No, 1, 2, 3, 4, 5, 6. Yeah, this is the sixth scheduling policy. It's called lottery scheduling. So in lottery scheduling, we give each task some lottery tickets. Now you can think of this as weights. The one that I talked about previously, right? So the more important my task is, the more lottery tickets my task gets, right? You can think of it at that way. So if I have two tasks and one of them is twice as important as the other one, I give the more important one twice as many lottery tickets as the other one. Now, how am I going to use these lottery tickets? I'm going to have a time slice very similar to round robin. So I'm going to divide time to time quanta. At the beginning of each time slice, I'm going to run a lottery, and one lottery will win, and whichever task that owns that lottery will be scheduled on the CPU. So if I run this algorithm again and again and again for so many time slices, what I would expect is, on average, each task gets as many CPU time, as much CPU time so the ratio between the time that two different tasks get on CPU should be proportional, or should be exact, as the ratio between their lottery tickets. If I have, if I have 5 lottery tickets and there are 10 lottery tickets in the system, on average, I should win 5 lotteries every 10 lottery. So I will get half of the time on CPU. Now, if somebody else has only 1 lottery, they're going to get, on average, 1 lottery ticket win every 10 lottery. So they're going to get 1 CPU, 1 time quantum on the CPU. I'm going to get 5 time quanta on the CPU on average. This is important. It's on average. So if I run this for a long period of time, then I can, have this good property that on average, the CPU time I get is proportional to the number of tickets I have. Now, you might ask, okay, how am I going to decide who gets how many lotteries? One thing is, you can just ask users to assign lottery tickets. So you can say, okay, users know about their tasks, so I can ask them which task is more important for you. Or I could, do those prediction stuff, right? I can look at tasks And if I realize that one task is shorter than the other, then I can increase their lottery tickets. So that's also possible, right? So somehow we need the lotteries to reflect the priorities of our tasks. So either it would be given to us by the user, or we make a decision on how to give them the lottery tickets. Now, this is good because we're not going to starve tasks, right? Because it's random. So even if you have a single lottery ticket and there are 100 lottery tickets in the system, you still have a 1% chance of running. So you're not, on average, you're going to run one time quantum every 100 time quantums. So you're not going to get starved. So I'm running out of time. I probably can finish this one. So here is an example. Let's say I have short tasks and long tasks, and let's say I have made the decision to give short tasks 10 tickets and long tasks 1 ticket. Now you can see that depending on how many short tasks and how many long tasks there are in the system, the CPU time of each one of them changes. So if I only have a single short task and a single long task, then the short task on average is going to get 10 divided by 11% of the time on CPU, and the long task is going to get 1/11. Now, if I only have 2 long tasks, then they're going to share the system half-half. So each one of them is going to get 50%. If I have 2 short tasks, they're going to get 50% each because they have the same number of tickets. Now, if I have 10 short tasks and 1 long task, then the short tasks are going to compete. They're going to get 9.9% each, and the long task is going to get 0.99. And if I have 10 long tasks and a single short task, the single short task is going to get 50%, and each one of those long tasks is going to get 5%. Now, if I have a lot of short tasks in the system, then they're going to compete with each other, right? So all of them will have the same priority, and it's going to get very similar to round robin with equal size, right? So this lottery ticket, lottery scheduling, if everybody has the same number of lotteries, in long term is going to behave the same way round robin was behaving. So, and if you remember, the response time was really bad, right? If you remember that example where we had a bunch of tasks with the same size, and then we divided we looked at round robin with 1 microsecond time quantum size, and then every task had really high response time. It was fair, but bad in terms of response time. So that same behavior could happen here on average, right? So this is going to be really good for fairness. You're going to be fair, but your response time is going to suffer. Okay, sorry, I went over time 1 minute, so I'm going to end here. Thank you for sticking around and attending the lecture. Thank you for those of you who are watching this afterwards. Take care, be safe. Talk to you after the reading week. Bye-bye.